Welcome to the class Optical Communication, Unit 2, Transmission Characteristics of Optical Fiber. In previous session, we have discussed what is intramodal dispersion and one of the type of intramodal dispersion, that is material dispersion, how to find the dispersion parameter, okay, with the help of group delay and group velocity. And here today we are going to discuss about waveguide dispersion. So the waveguide dispersion originates from the variation in group velocity with wavelength for a particular mode. So as we all know, waveguide dispersion is one of the type of intramodal dispersion, so that commonly occurs within a particular mode. In terms of mode analysis, the waveguide dispersion arises because of the dependence of propagation constant with wavelength. Hence, I can write this relation with an equation d square beta divided by d lambda square, which is not equal to 0, because your dispersion is totally depends on your propagation constant. Okay. So now we are going to find out the waveguide dispersion parameter dWg. Okay. So in order to find dWg, first we have to find what is the RMS pulse broadening due to the waveguide dispersion. Okay, how to express the RMS pulse broadening due to the waveguide dispersion. So this equation I am going to write with the help of group delay and group velocity. Okay, already we have learned how to write the equation for group delay with the basic formula distance by time is equal to distance by velocity. So tau g is equal to L by Vg. Okay, when I substitute Vg, you will get your tau g, that is your group delay. And your waveguide dispersion, that is your tau Wg is equal to L by C into dB by dk. That is, we already seen that your waveguide dispersion is totally depends on your propagation constant. That's why I am writing this equation. Now in order to express your RMS pulse broadening equation, sigma Wg, which is approximately equal to modulus of d tau g divided by d lambda into sigma lambda, where sigma lambda is your spectral width. So from the equation tau Wg, okay, we can get sigma Wg. If I have differentiate with respect to lambda, you will get sigma Wg. Okay. In order to find the waveguide dispersion parameter dWg, okay, your formula is 1 by L into d tau g divided by d lambda. Already we have obtained this d tau g divided by d lambda. Substitute and you will get the waveguide parameter expression. Okay, so from the expression you can understand that your waveguide dispersion is also depends on the wavelength and also the propagation constant. So till now we have seen what is intramodal dispersion and what are the types of intramodal dispersion and how to find the dispersion parameter. Okay. Next topic is intermodal dispersion. Intermodal dispersion arises from the propagation delay difference between different modes in a multimode fiber. So this intermodal dispersion is commonly occurred in multimode fiber. Okay. The intermodal dispersion which causes pulse broadening essentially arises from the difference in time. Okay, that is T max and T minimum. That is nothing but time delay between the lower order modes and time delay between the higher order modes. Okay, that is T maximum and T minimum. Pulse broadening due to intermodal dispersion is most significant in case of step index multimode fiber. Okay, this can be controlled to a great extent by using the gradient index profile. Okay. So what it says, intramodal dispersion is commonly occurred in step index fiber. Okay, in order to overcome that, we have to use gradient index multimode fiber for more applications. When optical fiber is designed to have a near parabolic refractive index profile, pulse broadening due to intermodal dispersions can be minimized. So what this says, if we have to select your alpha value, that is your refractive index profile value, okay, which is equal to 2. That is for parabolic refractive index profile. Okay, if I select that profile, we can minimize the intermodal dispersion. Okay. Single mode fibers on other hand do not suffer from the pulse broadening arises from the intermodal dispersion. So intermodal dispersion will not occur in single mode fiber. It will be commonly occurred in a multimode fiber. Okay. So it occurs in both type of multimode fiber, multimode step index and also in multimode grade index fiber. So let us see how this dispersion is occurring multimode step index fiber. Okay. So this is a ray diagram in a multimode step index fiber showing the path of aerial ray and extreme meridional ray. Okay. The aerial ray, the ray that passes along the origin, or the meridional ray that follows the total internal reflections. Here both ray travels with the same velocity through the core region having constant refractive index. The delay difference actually arises from the path difference between the two rays. The time taken by the axial ray to travel the length L along the fiber is T minimum, given by T minimum is equal to L by velocity of the light in the medium. Okay. With the basic formula, T is equal to distance by velocity. I am writing T minimum, which is equal to L, that is the length of your fiber. Okay. Or the distance traveled by the axial ray divided by velocity of light in the medium. Okay, so T minimum is the time taken by the axial ray and T maximum is the time taken by the extreme meridional ray. Okay, so I can write the T minimum as L by C by N1. Okay, C by N1 is nothing but your velocity. Okay, if you where N1 is the core refractive index and C is the velocity of the light in free space. The maximum delay time, that is your T maximum, is obtained. Okay, is obtained from the meridional ray. So T maximum is equal to, with the same formula, L by velocity of light in medium. So here your ray follows the total internal reflection. That's why your velocity is written as C by N1 into cos theta. Okay, so if you substitute, you will get Ln1 divided by C into cos theta. So applying Snell's law at the core cladding interface, we all know N1 cos theta equal to N2. Okay, so that is cos theta equal to N2 by N1, where N1 is the refractive index of core and N2 is the refractive index of cladding. Okay, so from substitute the value of cos theta from equation 4.76 into 4.75. Okay, you will get your T maximum. So now we will get what is T minimum and T maximum. So with this I am going to find the delay difference between the two extreme rays, that is your axial ray and also your meridional ray. So your delta T mod, that is nothing but a delay difference, is equal to T max minus T minimum. Substitute both the equation, you will get your delay difference. Okay. So with the following assumption, let us consider the del value is very, very small. Okay, and your N1 is approximately equal to N2. Okay, why I am considering this two assumption now? In order to reduce your dispersion. Okay, so if I am substituting this two condition in your above equation, you will get your del T mod is equal to L N1 square del divided by C N2, and of course if your del value is less than 1, your numerical aperture for a step index is equal to N1 into root of 2 del. Okay, if you substitute, you will get your delay difference is equal to L into Na the whole square divided by 2N1 into C. Okay, so here in place of del, okay, that is in place of N into del, I am going to substitute the numerical aperture formula. Okay, so this is your intermodal dispersion. Okay, delay difference for your intermodal dispersion. Now the RMS pulse broadening, in case of RMS pulse broadening, the delay difference derived above can be used to estimate the broadening of the pulse caused by intermodal dispersion. For this purpose, it is necessary to assume the shape of the pulse initially launched into the fiber. Okay, so we have to consider a square pulse. Okay, the square pulse within the range minus d mod by 2 to plus d mod by 2. Okay, with the PDF value 1 divided by del T mod. Okay, so this is your unit area. With the help of this assumption, we have to find the RMS pulse broadening. The RMS pulse broadening due to intermodal dispersion can be obtained by considering the rectangular pulse of unit area as shown in your figure. The rectangular pulse can be assumed to have a height of 1 divided by delta T mod and the width of delta T mod ranging from minus delta T mod divided by 2 to plus delta T mod divided by 2. Okay. So the total area of the pulse remains unity. Okay. So with this definition, we can write this formula: integral of over a range P of t into dt is equal to 1. Mathematically substitute your P of t. Okay, so P of t is nothing but your within the range your value is 1 divided by delta t mod. Substitute and we can define the equation for RMS pulse broadening. Okay, then with the help of mean square value, nothing but the variance of a pulse broadening due to intermodal dispersion can be obtained as sigma square mod is equal to m2 minus m1 square. As we all know, we will consider a zero mean. Okay, so m1 is the mean value and m2 is the variance value. We know the equation for mean and also we know the equation for variance. Okay, here considering zero mean and variance, and with the variance value m2 is equal to integral minus in plus infinity t square p of t by t into t. Okay, now for the given pulse I am going to calculate the variance. Okay, so variance is equal to 1 divided by delta t mod. Just substitute. Okay, you will get variance. Okay, so what is your RMS value? So sigma mod is equal to 1 by 2 root 3 into d mod. Okay, substitute the d mod value from equation 4.81. Already we have calculated what is delta t mod. Substitute this equation here. Okay, you will get the RMS pulse broadening due to intermodal dispersion.